Hello. We will wait for 5 6 minutes and then we will start. Okay. Good evening, everyone. So, my name is Abhishek Munshi. I am a PMRF research scholar at IIT Jodhpur, and today is the week 6 of our lecture Design of Power Electronics. So, today we will discuss about the inductor design. So, as this is a very critical topic in designing a power converter, because always we require a inductor while designing a power converter. As we know that in case of the power converter, we have a filter inductor, we have boost inductors, and even we have flyback transformers. Those all are into the group of the power inductors family. So basically they all functions by taking energy from the electrical circuit and storing it in a magnetic field, and subsequently that return this energy excluding the losses, and then send it back to the circuit. So this type of inductor which are grouped into the power inductor family, we will discuss how to design the inductor with a simple example. Okay. So basically, moving before moving into the inductor design, we will discuss some basics like which we all have studied previously in other courses, mainly in machines. There's a magnetic circuit. We'll discuss it in a little bit, and after which we will move into the inductor design. But the main thing is that you have to keep it in your mind that while designing a power inductors, you should have to consider some factors like operating frequency and ripple currents. Okay. So these power inductors may be of single winding, into which you can see the output filters of inductor that is used in case of, for example, buck converter, boost inductor, okay, and flyback inductor in case of the mm, buck boost converter. Eg- And also, apart from it, we also used input filter inductor in case of the converter. So these all are grouped into the single winding inductor. And in case of the multiple winding inductor, which we are called it at the flyback transformer, for example, or coupled output filter inductor. So these all are grouped into the multiple winding inductors. Okay. So for all this inductor design, you have to keep it in your mind that we should have to consider the factor like operating frequency and the ripple current. So basically, uh, we know that there are DCM and CCM mode of operation of converter. So obviously, in continuous conduction current mode, ripple current is often small enough that AC winding loss and AC core loss may be significant, but in the discontinuous, the AC losses may dominate. So we have to consider in this way for designing the converters. Okay. So now we move into the basics of the. We'll revise it in a quick manner. The basics of magnetic circuits. So the fundamentals of the magnetics. The basic, that number one is the Ampere law and MMF concept. So basically, what is MMF? So so what is MMF basically? So wait, yeah. So MMF, its full form stands for magnetomotive force. So here we are seeing a simple structure of a inductor, where you can see that this is the core of the inductor, where wires are winded. Okay, and whenever there is a wire are winded, so the current will flows through it, right? Sorry, yeah. So it will produce magnetic field, Okay, so moving into the first topic, that is what is magnetomotive force basically. So we know that in case of an electrical circuit, if we consider an electric circuit, we have resistors. So in electric circuit, we know that current is induced due to the existence of EMF. EMF means electromotive force. Okay, so we know that in case of the electric circuit, due to EMF, current is produced. Similarly, in case of the magnetic circuit, magnetic flux is produced due to this MMF. Okay, so this MMF, which is denoted by this symbol AF, that is equal to N into I. That means number of turns into the current flowing through it. Okay, fine. So basically, what happens in MMF is proportional to the current. Okay, so this MMF is proportional to current. So that is equal to Ni, where N is the number of conductors binded to number of wire windings also. Okay, so it depends. Okay, so mm, this can also be written as H into LC. Okay, so what is basically H? H is basically the magnetic field strength or intensity. H is basically the magnetic field intensity, or in sometimes we call it as magnetic field strength. Okay, the unit of H is, let me add a slide. This H is thus ampere turn per meter. Okay, so that's why in last slide I wrote that, yes, slides are not visible. I think it is visible. Mm, now it is visible. Is it visible? Kindly answer. Okay, fine. So where I was there, yes. So H is basically ampere turn per meter, which can be written as F by LC, where this is the length of the magnetic circuit. Okay, and this F is basically our MMF. So MMF can be also written as H into LC. Okay, so finally, you can say that H has an unit of ampere meter or ampere turn per meter. Okay, so H amp per meter. Some book you will see amp turn per meter. Okay, fine. So now next thing we have to understand, that is the permeability. Okay. Basically, permeability of free space, that is mu zero. Mu zero is the free space permeability. Okay. So how could you understand what mu zero is? Basically, it is derived from the BH curve, the above BH curve. So it says that this B is proportional to H, where a constant is coming as mu zero H. Okay. So this constant is called the free space permeability. That can be in in a simple way you can say that this permeability is nothing but the inductance capability. That means the since its unit is also Henry per meter, it's basically determine the how much inductance your magnetic field has. Similar like in case of the kindly mute yourself. Manish Kumar Puri, kindly mute yourself. Okay. So where I was there that yes. So I was saying that it basically determine the inductance of the magnetic field, just like in case of the permittivity, we determine the capacitance of the electric field. So how much capacity the electric field should have. So this is basically how much inductivity in electric magnetic field should have. Okay. So that is what the permeability of free space is. Basically, this is Henry per meter is unit. Okay. And from here you can see that this is the way to understand step by step that I into n by lc, that is h. Why? Because we came into from the first slide that f equal to ni, so from I n into lc we can write it as the h. Okay, so similarly since h is mu a into b, you can write it like that. Okay, fine. Now, what is B basically? What is this B? Okay, so adding a slide to understand it. So this B is the magnetic flux density. The flux density, that means flux per unit area. This is flux per unit area. Area in the sense here, the cross sectional area. Okay, so the unit of flux is Weber, and area we all know that is meter, so that will be the unit of B is, that's why Weber per meter square. Okay, since area is meter square. Okay, so H, which is the magnetic field strength, can also has another unit, that is from here we also state that it is ampere per meter. Okay, clear? Now one another thing which we see in the last slide, that is the relative permeability. You should have to understand this relative permeability. that is mu r. So as I said that B is proportional to H, so it can be written as mu H, okay, and that is mu R mu 0 H. So that means this mu R, which is the relative permeability, is basically mu by mu naught. So this is the ratio of the absolute permeability by the permeability of vacuum, or we can say that the free space permeability. Okay, so this mu is the absolute permeability, and this is the free space, that is for vacuum, and this is the relative permeability. Okay, I'm just revising the basics of the magnetic principles and circuit, and then we will move into inductor. Okay, so this mu, which is basically mu r mu naught, is the absolute permeability. Okay, so for air or non-magnetic material, the relative permeability should be 1. You know that for air, non-magnetic material, mu is 1. Okay, but in case of ferromagnetic material, it should depend, so it should have a value. Okay, so after this, if you have any doubt, you can ask, and we will move into the next slide. Fine. Okay, so before moving into this one, so magnetic flux, as I said, that magnetic flux related to this phi s, that this is area of cross section. So we, as I said, that V is phi by AC. So B into AC will give the flux. H into mu will give the magnetic flux density, where H is the magnetic field intensity. So this is the easiest way to understand these things. Okay. Mm. So next thing is that the how much inductance it should have in the circuit. So which can be determined by this lambda, where flux into N will determine this magnetic inductance. This is the flux linkage and inductance. So finally, this flux linkage, which we defined in last slide, this is flux linkage. Okay, so it can be related as this inductor. So this is basically I into L can be written as N square by LC mu S. Okay, so this is the basic formula we derived from magnetic principles. So how could you relate it? Okay, so fine. So magnetic circuit, if you see here, is basically analogous with respect to the electrical circuit in the way that in electrical circuit we have resistance. Okay, here we have this R, this is reluctance. Here we have current, here we have flux, here we have EMF, and here we have MMF. So this is the analogy between electrical and magnetic circuit. So what is basically reluctance? You have to understand this. From this analogy, we can define that reluctance. What is resistance? From Ohm's law, we said that resistance derived V by I, right? Where V is EMF, right? So from magnetic circuit, we can say that uh, this see F, that is the MMF, is equal to I equal to VA, right? So if this is equation 1 and if this is equation 2, dividing 2 by 1, we get pi by F, that is equal to HI by, sorry, VA by HI, right? So B can be again written as mu 0 mu R HA by HI. So H can be cancelled out and can be written as A by I. So thus, from electrical circuit, we can define reluctance as MMF by flux, right? So considering equation 3 and 4, we can define reluctance as I by mu 0 mu R A, or in a sense can be replaced by absolute permeability mu A. So that is what the reluctance is. This is reluctance. Okay. Thus, reluctance is nothing but resistance in case of our electrical circuit. So, is this clear up to this? Try to note it down, and if you have any doubt, you can ask. Okay. I'll give you 5 minutes to note it down. Okay. I hope you all understand up to this. And next is Faraday's law. Okay, let's skip that. Okay, so Faraday's law. So basically, Faraday's law, we all know as an electrical engineer that basically whenever there is a change in your flux, that will create an EMF, right? That is the Faraday's law. And if you include the Lentz's law, we said that the induced current produces magnetic fields which tend to oppose the change in the magnetic flux that induces such currents, right? So basically, it says that the induced current opposes changes in the initial magnetic
नहीं
field.
मैं ना मैं वहां से छोड़ दी ना मैंने।
So I warned many times Manish Kumar Puri. So I have to, fine. So Lentz's law, it said that the induced current opposes changes in the initial magnetic field. Okay. So combining these two, the Faraday's law, we put a negative sign over here, minus d phi dt and d phi dt, which can be again written as L di dt as inductance, right? And this is the self inductance, and also we have another kind of inductance, mutual inductance, whenever there is to be the and that is the inductance between these two. Whenever we have a transformer, we have two coils, right? So that will be the mutual inductance in between of that, right? If you have a coil, right, like you have a coil like this, so it has a self inductance. Suppose L1, it has a self inductance L2, and between of this we have a inductance created that is called mutual inductance. Okay, fine. Uh, so now the next thing we have to understand, that is the air gap. So from here, you see that I derived it, that we already got the reluctance as uh, how much we derived it at I by mu a, right? So fine. So it can be again written as, so this is the area of cross section. Okay. So here I put I, and in the first slide, this I is basically what in the first slide I put it, right? This is length of the magnetic circuit. So you can don't, that is not current. So I'm changing it to LC. So that will be better done. This is not current. Okay. Right. So for confusion, since I put here I put it that like not right. So reluctance is basically LC by mu AC, which we derived already, right? So from here, this is the core reluctance. Okay, and from here we calculate the how much air gap we should maintain and not, right? Air gap essential factor, because while determining the pH curve, it is very important. We have to understand this and losses. The next is the magnetic losses. As I said, that another thing that's important, that is magnetic losses. So you should have to understand that. So this is a VH curve. So we have to discuss a little bit about VH curve. Otherwise, it will not be easy to understand. So VH curve is basically the magnetization curve. So this curve basically gives the relation between B and H. So as you see here that it is not a straight line, right? So here you can see that we see that V equal to mu H. So from if something is proportional to H, we naively expected that it will be following a straight line, but it is not a straight line. So it is a non-linear curve, not a linear curve, right? As it is expected from the equation, it is not like that. So there is a factor mu which we add over here is very much typically depends upon this h, so that's why it is not a linear curve, it is a non-linear curve. So this BH curve is often described as the hysteresis loop. Okay, so why this is called hysteresis loop? Because from the here you can see that it is energized for up to a certain time and then it is demagnetized. So it requires magnetization and demagnetization process performance. So it has to perform the we have to require energy to magnetize it, and again we have to require energy to demagnetize it in a loop. So that's why it is called a hysteresis loop. So I'm not moving into deep into it. You can see that when it started from a point and it's ended after whenever your b is getting 0 is h is not getting 0, whenever h is getting 0 b is not getting 0. So some residual magnetism phenomena is there, that is due to the corrosivity and retentivity factors. So I hope you should know these things before. So since the corrosive force and will be a factor, that's why at h equal to hc that here the b is not getting 0, right? So these are the factors. Another factor is the retentivity. So another thing is that whenever you can see that is discharging is not following the same path, that is due to the phenomenon of non-conformity, or you can say that non-overlapping phenomenon. That is why the increase and decrease curve is happening, and this is the hysteresis loop forming. This area is forming the hysteresis loop. Okay. So now, based on the material, magnetic material we selected, uh, this hysteresis phenomena will differ. This is slim in some cases. For example, in case of ferromagnetic materials, it will be look like a so broader, like this. Okay. In case of silicon steel, it is lesser than this ferromagnetic materials alloy. Okay, like alnico, this type of alloy have a different VH loops. Okay, so basically hysteresis caused by in a simple term, if you have asked why hysteresis happened, this is due to the cyclic magnetization and demagnetization process that leads to some magnetizing energy to be lost. Okay, now this loss of energy is kind of two types, that is due to the winding loss and that is due to the core loss. Okay, the core loss can be again subdivided into two parts, that is due to hysteresis, another due to the eddy current loss. Fine, so a little idea about it. So what is hysteresis loss thus? So hysteresis loss, as I said, it is caused by cyclic magnetization, demagnetization, that leads to some magnetizing energy to be lost. Okay, so if this is the empirical formula for hysteresis loss, okay, where this n is the Steinmetz constant. I hope I showed it here. No, here it is. So this is the Steinmetz constant. Okay, so it is between 1.6 to 1.6 to 2. The Steinmetz constant. Okay. Another loss I said, that is eddy current loss. So eddy current loss, why it happens? Because we know that the magnetic core, the core of the magnet is solid, right? So there, so since magnetic core is solid, there eddy current loss may happens. So why? Because it can produce eddy currents due to the excitation of AC magnetic flux, which is induced by the voltages as a result of the Lenge's law. So this loss can be reduced by using laminated core. In case of transformer, you can see that often they use laminated cores. Okay. So this, the expression for the eddy current is K is the current factor Pm square. Okay. In case of hysteresis loss, it depends upon Steinmetz constant, but here it is square of it. Okay. So this value of K getting lowered and lowered whenever we are using this kind of laminated core. Okay. So these are the basic losses in case of magnetic losses. So what are the factors about the magnetic losses? We said that it has two losses, winding and core losses. Hysteresis and eddy losses are into the core losses. Winding losses included DC and AC resistance losses. This is the DC resistance, the AC resistance. This is the DC resistance power loss. This is the AC resistance power loss. So AC resistance is due to the skin and proximity effects. Okay. So from here you can say that there are other than this there are winding losses also, right? So what are the losses we conclude? Uh, One is the core loss. Okay. Another one is the DC resistance loss. Write it like R. Another one is AC resistance loss. So DC resistance loss, how it can be calculated? It can be calculated as IRMS square into the DC current resistance. Okay. This is basically the DC resistance of the inductance. The inductor, and this is the RMS value the peak current which is applied to the inductor. Another type of loss is that AC current, AC resistance loss, and so the wire loss which is caused by AC resistance is more difficult to calculate, as we know that AC winding resistance values are not always available from the magnetics. From if you are buying a core from any company, magnetic company, then not often gives you the value of the AC resistance. So it will be difficult, but if you have the value of that AC resistance, you can calculate it similarly like before. We calculate the DC resistance is I RMS square into the AC resistance of the inductor. Okay. So, as a conclusion, we can say that the total loss in case of an inductor is basically the sum of all three losses. Okay, clear? So, if you have any doubt regarding these losses, you can ask, and then we'll move into some basics of inductor design. So, try to note it down, and if you have any doubt, you can ask. So fine, I hope you all understand these things. Next, we have to consider the type of conductors. While designing an inductor, we have a core and we have to wind the wires around it, conducting wire. So it can be of two type, three type. One is single strand wire, can be multi-strand wire, can be string leech wire. So this is the standard wire looks like, and this is the leech wire look like. Okay, so it has a bundle of conductor accommodate into a single conducting wire. Okay, so while choosing a conductor, you have to keep it in your mind that what kind of wire you are choosing, standard or lead wire. So lead wire is basically preferable in high frequency uh, transmission, like in wireless power transmission we prefer lead wires type of uh, for designing the coils, inductance. Okay, another factor you have to keep in your mind while designing, while choosing the wire, that is the size of the wire. How much AWG wire size is at? AWG, which stands for American Wire Gauge, that is a fundamental basic standard for choosing the wire. It can be ranges from AWG 40 to 18 as we are moving into this AWG 1 2. Okay, so it will be more and more wider, thicker comparative to this higher values. Okay, so keep it in your mind that how much current it draws, and based on which you have to decide how much AWG wire you are choosing for your inductor. Okay, So based on which you have to decide that, and how much frequency you desired to be on the inductor, based on which you have to choose the wire type. Okay. So the characteristics of magnetic material which are desirable for inductor design, we already discussed those terms to understand that what are the desirable characteristics? One is we require high unity permeability, require high saturation flux density because so that the inductor not get saturated before the flux reaches to the expected value. High electrical resistivity, high Curie temperature, low core loss density, and high maximum frequency. So it should have maximum frequency very high. It should have low core loss. It should have high relative permeability, saturation flux density, electrical resistivity, and all. Okay. So these are the desirable characteristics required for a magnetic material for choosing or designing the inductor. Okay. So now the next thing that uh, to consideration of the core. So as we know that ideal magnetic materials cannot store energy, but the practical magnetic materials which store very little energy. Okay, so uh, as I just store little energy because most of these practical magnetic materials ends up as a loss. Okay, so in order to store and return energy to the circuit efficiently and with minimal physical size and small non-magnetic gap is required. Okay, so for designing the mm, uh, inductor, so that's why we require high permeability magnetic core material. So in case of ferrite or laminated metal alloy core, the required gap is physically discrete. But in powdered metal core, the gap is distributed among the metal particle. So you can paradoxically say that virtually all of the magnetic materials, magnetic energy is stored. So called the non-magnetic gap. Okay. So basically, we require uh, a proper material core like ferrite base core for designing the inductor so that it can store energy. So consideration of the uh, core while designing inductor is one of the basic factor. So core may be of many types. You should have a rounded core. You should have E core. You should have EE core. A lot of cores are there. So based on which you have to design the core materials. So we have to choose it from the data sheet. As you see that I am giving here a data sheet for ETD29. This is a E core. It may be have some factors like this. The values will be given on the data sheet. This is A, this is D. From here you can see the mm, length of those parts of the core for a specific E core ETD29, this is ETD34, and also you can able to understand how much ADI it has, how much window factor it has, air gap it has. Okay, so you should have to keep all these factors while designing the inductor. Okay, so number one, the magnetic core. It has many geometries, as I said, E core. Okay, it's maybe like this. The core may be like this. The core may be like this. Core may be like solenoidal. A lot of type of cores are there, and based on which inductance can be calculated different way. So it dimensional and design data you should have to know, and the window utilization factor that can be written as this is the NAW by WA, where WA is this volume and this is the window area. Okay, AW is the window area. So window factor is utilization factor is KU. So these are the formulas. I have to put it down in a copy to solve some problems. So in case of core selection, and you have to keep this in your mind that first of all, based on your design, you should have to decide the shape and size, right? And after which the factors, the inductance calculations, how can be done by those cores. You have to put those values and all, right? So next thing, the this area product for inductors. Here you see that it can be written as this formula. I think you go through the lecture of this week and you can easily able to understand these things. So this is the AP factor, and fine. So these are the formulas. So now moving into inductor design. So step by step we will revise how to design the inductor. So number one is inductor design. The process is inductor design using this area product method. Okay. So number one is design specification. You should have to understand what is the value. You should have decide what is the value of your inductors. How much average inductor current flowing through it. How much current ripple you will allow for designing that inductor. What will be your output power? What is your switching frequency, based on which you have to decide the wire. How much current density, based on which you have to decide the wires, to decide the core. Okay. How much window utilization factor you have, how much temperature rise would you allow for a design, uh, what will be the operating flux density, what type of material you are required based on your frequency and your setup and your conditions, what type of core materials is this so first of all, this design specification we have to understand from the data sheet that how much current we have, what to choose. Okay, like this. Okay, next thing we have to calculate the area product. So this is the area product. So that can be written as uh, L I L peak. There is a peak current of the inductor. This is the utilization factor. This is the magnetic flux density, and this is the current density. Okay. So first we have to calculate this to decide the design. Then you have to calculate the area product of it. Okay. Next, we have to select the core. After calculating the area product, we have to select from area product, we have to select the core. If we have area product, suppose 0.114, around that. So we have to choose this value based on which we have to decide that we have a core EE187, have to decide. Okay. Next, we have to decide the wire. How we can decide the wire? We know that the window factor from the window area, that is basically the inductor RMS current by the current density, right? So basically this current density is ILRMS by the window area. So from AW we can get it from the, after selecting the core we can get AW, and we have the current decided, and based on which we have to calculate the GM, or we have, after calculating that, after deciding the current or current density, we have to choose based on which how much AWG we require. For example, if we have got an area product of suppose 534.8, so we have to decide that AWG 0 will be best. Okay, so that is how we have to select the wire. After selecting the wire, we have to decide how much turns it required for the inductor. We have the core, we have the wire. Now we have to turn the wire into the core. So how much wire turns we require? So that's why we have to calculate it, that N equal to Ku, this window utilization factor, this WA by this window area, right? So that is how we have to calculate the number of turns. Okay. After we have the number of turns, next factor what will arise that how much air gap we have to keep in that. So air gap, as I discussed already in the magnetic circuit design, that air gap we have to calculate by these formulas. The next step is to decide how much air gap we should allow. Okay. After which we have to check our design. We have to put the formulas. I have to check that whether it will satisfy the BH, how much it will have the peak flux, magnetic flux density, and average magnetic flux density, how much magnetic flux density we are getting for our core of the material, and based on which we have to decide that how much peak current is going in our inductor and how much repel we will allow as we decided previously. So how much repel is allowable in our design. So that is how all our factors we have to decide. And after which we have to check these design checks. Next is operating flux density and how much power loss we can adhere to for the design and how much temperature rise will be suitable for our design for our converter. So we have to keep all this mind in your mind before designing a converter, the inductor of the converter, right? So that's all are the mm, uh, magnetic basics and the design procedure of an inductor, which you already had learned in this week, and I'm just discussing it in a more briefer way. So if you have any doubt, after which we can ask, and after which we will solve a problem based on which we will end it. So if you have any doubt, you can ask. Then we will move into a problem. So you can ask question. If you have any doubt, I'm giving a question. So I give two questions, try to answer it. And if you have any doubt, you can also ask that. Core loss of magnetic material depends on which of the following factor. And as the operating frequency of sinusoidal current through the conductor decreases, the skin depth will what increase, decrease, or remain same. So try to answer these two questions. So that was a very easy set of questions. So the core loss of the magnetic field obviously depends upon all these factors: the frequency, flux density, magnetic materials, volume, as I already discussed, and then the operating frequency of a sinusoidal current will obviously increases. As if it decreases, the skin depth will be increases. Okay. Next two question, try to answer it. Which of the following is true? And try to answer this in the comment box. Fine. Yes. So, so obviously it was correct. Which of the following is true? Yes, the higher the skin depth, lower the resistance. What statement hold true for AWG? So it will value decreases as AWG value decreases. Obviously, diameter and area increases. For higher value, it will be lesser, as I shown in the chart. And resistance obviously decreases in case of the high conductor. The magnet maximum current rating obviously it will increase since it has a more area, right? So next set of question is that we have it will be a for a buck converter. The inductor value is 80 microhenry. Okay, the current rating is given as 15 ampere, and the ripple limit is given as 0.5. The magnetic density is given 0.3 Tesla. Density of current is given. Window fill factor is given. So these are the values which are given. I have to calculate the area product. Okay. So try to calculate it by the formula I already showed, giving 2 minutes. So we will solve the basic factors of the inductor by this problem. Okay. So try to solve this. I'm giving 2 minutes. So based on the formula, you have to calculate it. So this was the formula that already discussed. The peak inductor current. What will the peak inductor current for a buck converter? We discussed it in the first class that that will be the current flowing through the conductor. Sorry, that will be the inductor current or the buck converter by the ripple by 2. So it will be 15.25 amp. And now energy, that is the half Li square, calculated as 9.3 watt. So now in case of area product, what will be the area product? 2 into W, this MWM, that is basically the energy by KU into BM into GM. That is the magnetic flux. This is the current density. This is window field factor. All the values are given. You have to put it. It is 6.2 centimeter to the power 4. Okay. So now let us consider that we are considering a ferrite core, EE ferrite core. Okay. So I hope you have given EE ferrite core data in your lecture on the magnetic core uh, for this week, and you have to write the part number of the ferrite core which you will choose. Okay. So if you have those data, kindly say. If you have the data of the EE core, kindly check that data and try to answer that which part number of ferrite core we will choose. Okay. Try to check, do you have the data that will be given, that was given in your lecture on magnetic core. Okay, fine. It seems like you don't have the data. So from the data, you can see that E is 75. Since we have the area factor, we calculated as 6.2. So it should have to be area factor greater than. So it should be close or slightly higher. So we are choosing more than that, that is 9.433. So that is E75 core we choose from this data. Okay. Now the next question, that what will be the window area? So you have to calculate it from the data itself. So you have this data. So from here we have to calculate the window area, that is 2.79 centimeters square. Okay. Next question, what will be the cross sectional area? What will be the magnetic pulse length? So we have this data. So try to answer this from here. So okay, I will help you one way. I'm just copying it, putting this here. Okay. Now try to answer this one. Okay. So I have given you the data. Try to answer it. I have given 2 minutes. Try to answer it in your comment box. So from the data, it can be clearly seen that the cross-sectional area for the 75 we choose is 3.7 centimeter square. The magnetic path length is 10.70 centimeter. So now next is we have to calculate the RMS inductor current. Okay. So I'm giving 2 minutes to calculate the RMS inductor current. So what will be the formula? Have you note it down in your copy? I expect that you don't note it down. So it will be IL square plus the ripple root over of it. That will be the RMS. Okay. So now try to put the value and tell me what will be the answer. So whether it is 3.37. So this is 15, this is 0.5. So what will be the answer? 3.37. How it could be 0.37? It will be around 15 ampere. Okay. So the next question, what will be the cross-sectional area of the conductor? Fine. So what will be the cross-sectional area? For cross-sectional area, the formula was okay. So you have to calculate this cross-section area, the window area actually. So you have this value and you have this J. So what will be the answer of this? To kindly answer it. So it was 15 and it is given 2. So why couldn't you answer it? 15 by 2, what will be 7.5 millimeters? Hmm. Next question, what AWG you have to choose? Okay. So from the data sheet, from the AWG's data, you have all these values. If you put check those values, you can see that AWG 8 will be the perfect for this. Okay, so check this AWG sheet. Okay, sorry. So on the AWG sheet, you can see the area as we calculated. The area is around 7.5. So this will be the better 8. So AWG 8 will be chosen for this design. Okay, fine. Now calculate the number of turns. Calculate the number of turns. What was the formula for number of turns? Just KUWA by AW. Try to solve it. Chandana, you miscalculated, I think. 0.186 or it is 18.6. Check the calculation. So if you put it, it will be 18.6, not 0.186. So it will be near around 19 turns because 18.6 turn is not possible, right? So how could you turn 0.6 time? So we'll choose greater than that, that is 19 turns of. Okay, fine. So if you have the relative permittivity, suppose 2300, what will be the air gap? Fine. What will be the air gap? So this is the last question. Try to solve it. So formula for air gap is mu 0 AC n square by 8. N calculated it as 19, right? Minus LC by mu RC. Okay. Try to put those values and solve it. This is the last question. Try to solve it. And if you have any doubt, you can ask in between of that also. Try to solve it. So what will be the value? So it will be, so putting the value, we'll get it around 1.87 millimeter. Okay. So if you have any doubt regarding the lecture, you can ask. Okay. So that's all. That's all regarding the design of the power inductor. So this is very crucial for designing any power inductor for our converter. So if you have any doubt, you can ask. Otherwise, we'll drop the class. If you don't have any doubt, you can leave the class. Right. So if you have any doubt, you can ask. Otherwise, okay, then try to solve properly, because silly mistakes I found here in the comment box. So that's all for the day. Good night.